Welcome to EDU World Space.
Here we're going to find the area of an ellipse, and the equation of an ellipse in standard form is x squared over a squared plus y squared over b squared equals to 1. And as we've seen, what this looks like is an ellipse with its long axis arranged symmetrically around plus or minus a equals x, and the same with y. And so, because of the symmetry, we need to integrate only in the first quadrant. And so we're grabbing 1/4 of the pi, so to speak. And so we'll integrate. There's a couple different ways to do this, but I am going to think about little columns or little rectangles, if you will, little slices in that first quadrant that have a width dx and a height that is y as a function of x. And so the area is the sum over those little d area rectangles, which is y of x times dx, with x going from 0 to a. Okay, just marching across, adding up slices. So we need to use the equation to find y as a function of x. And I should also multiply that area by 4 because I'm just finding with the integral the area in the first quadrant. Okay, so that 4 is for all 4 quadrants. Kind of imagining the rest of the ellipse taking up the same amount of space in 3 other quadrants. Anyway, we can solve for y as a function of x. That's not hard to do using the equation. And we get y is equal to b times the square root of 1 minus x squared over a squared. And we don't have to worry about the plus or minus because we are in the first quadrant where both x and y remain positive. That is the reason for doing this. Anyway, the area is now 4 times the integral x equals 0 to a times b. We can bring the b out. Let's do that. Makes life look a little bit nicer. But we have the square root to integrate over. And often with the square root, you can make a trig substitution. So that's what we're going to try. We're going to try to let x over a equal to sine of theta. And we can do something like that if we're sure that the x over a remains equal or less than 1. And we're guaranteed that, so we're good. And if we take the derivative of both sides and kind of work with it a little bit, we get dx is cosine theta times a d theta. We can work on the limits as well when x is equal to 0. We must have theta equals 0. And when x equals a, theta has to equal pi over 2. And so the limits are easy to work out as well. And this is where the trig substitution is really useful. because we can see that what we have in there is 1 minus sine squared theta to the 1/2 power. And that is the same as cosine theta. And again, we don't have to worry about the plus or minus because we are in the first quadrant. Now, there are several ways that you can finish the integral of cosine squared of theta d theta. But I usually like to use a little trick. As long as you are completing a full quadrant, whether it's 1 quadrant, 2 quadrant, 3 quadrant, or 4 quadrant, then you know that the cosine and the sine contribute equally to that. And so I usually like to imagine that I had the full integral of cosine squared plus sine squared over that interval. And I know that they contribute equally. And so the integral of just the cosine part is just 1/2 of the full. And again, I want to point out that this is true only if you've gone through a full number of quadrants. If your angle stops in the middle of a quadrant, like pi over 3, pi over 4, you can't use this trick. But we also know that the cosine squared plus sine squared is equal to 1. And so we can do the full integral on the right-hand side. And that is just 1/2 times pi over 2, or pi over 4. So again, a good reason to integrate over a quadrant. But using this result, we can now see that the area is 4b times a times pi over 4, or pi times b times a. And this is kind of a nice interpretation. So an ellipse is kind of like a squeezed circle. And for a circle, the area would just be pi r squared. So this is kind of nice that we have sort of like an r squared, except with 2 different radii. And so this is often a way to interpret the area or to remember this formula.